Awesome.
Yeah. Hi, everyone. My name is Wayne from Niekerk. I'm here from Protea, Community Manager. I'm just going to give you guys a little bit of context behind the Protea UI, as well as the core architecture of Protea Gather. And that'll kind of lay precedence for Ben's presentation going forward in terms of the front end and back end coding functions for the token bonding curve. I'm just going to share my screen quickly. Just give me a second. Go back into Opera. Let me know. It should load now. Cool. Yeah, so for any of you guys that are interested, Protea Gather is what we're looking at the moment. And this is the first dApp built on the Protea X protocol that we are currently developing. With Gather, we are actually building a tool that helps communities grow by visualizing their social capital, as well as incentivizing sustainable engagement with tokens. So last week, Thursday, Protea managed to launch Gather in beta on mainnet. And anyone on this call, if you want to, you can do the same. Type in gather.protea.io and you'll be able to explore our system on mainnet, as well as any of the other test nets such as Rinkeby. And what we're looking at here in terms of the system is just the basic straightforward dashboard of Protea Gather. And essentially, excuse me, sorry. And on Gather, you have these community markets, and these community markets are represented by a token bonding curve. And you can buy into any of these. So your buy-in essentially is what your social capital is that you hold in that community. And the collateral for all token bonding curves on Protea is represented in DAI. And just from a UX point of view, we're experimenting with always representing the value stored in communities as DAI. So if you look here in Token Engineering Cape Town, which was the launch event that we kind of ran our event off last week on, in this community, you'll see the market cap, which is currently how much has been staked into this community for Token Engineering Cape Town. And then my own personal stake, or what you could say is my own social capital that has been invested into this community, is 20.64 DAI. And you can see here in past events, essentially what that DAI is my skin in the game, which I've actually wanted to invest in. And I can use for this event, which has already happened, and this event that's happening up the next week, I can use to further RSV and partake within this community. And essentially, this is just a proof of attendance, which is collected and obviously will be redistributed towards the end of the event, which you can get back for committing or showing or proving your attendance. Let me just stop the screen share here. Ben, if you wouldn't mind just showing the core architecture slide.
Sure thing.
So is that?
Can you see it?
No, it's just on the screen share mainnet. I think you need to go slide.
Oh, right. There we go. Cool.
Cool. So on Gather, on-chain, any community currently has a set of 3 contracts. The first contract is obviously the token bonding curve itself, which regulates the buying in and out of a community. Then next to that, we have the membership manager, which actually acts as an abstract or middleman between the token bonding curve and what we would call the event manager. So when joining a community, tokens are actually stored in the membership manager. And when RSVPing to events, the membership manager reserves tokens for that event and then redistributes stakes based on proof of attendance. The skin in the game interaction between your membership stake and events could obviously easily be replicated into other utilities, not just RSVPing. So for example, putting skin in the game to signal that you perform a service, like a service for your community. And then obviously adding other utilities later on could be facilitated by a separate contract for migrations. In other words, creating like a community factory of sorts to build a rebate system or a few other things beyond just RSVPing. However, on the token bonding curve, this is pretty much what the rest of this presentation is going to cover. So we're going to deal with some front-end calculations, which are currently done in JavaScript, and then the actual token bonding curve contract, which is currently done in Solidity, and it's pretty much a custom repo that Ben and the team have been developing. So Ben, without further ado, you'll take it away.
Cool, thanks, Wayne. Cool, so yeah, after our mainnet launch, we had a few pain points in our workflow, and we learned quite a lot about the process and how we would like to organize our code base in future. So we had some functions in the front end and back end implemented in JavaScript. A lot of that code you had to use JS big numbers, and big numbers don't handle floats very well. You've got to do things like scaling, like you would have to do in Solidity, and it just doesn't lend itself to very readable code. You get long strings of multiplication and division. Once again, something that you see in Solidity quite often. So yeah, trying to implement math-based logic in JavaScript was problematic. On the other hand, the Python code, these are the basic bonding curve functions. It's more readable, and it's a lot better suited to doing these sort of calculations. So looking at the Solidity contracts, once again, we had a slight update to one of our curve designs, and it started introducing more parameters. We started getting negative values within the calculations and getting underflows with Solidity safe math library. And once you start having to do scaling and you start hitting overflows, and anyway, lots of issues with it, which can be handled, but it results in, once again, very unreadable code, difficult to maintain code. And if you had a workflow where you were starting with Python code, a better solution would be to use something like Viper, where it can be more directly transferred. So yeah, Viper has built-in handling of decimal points, not necessarily floats, but it's also can handle negative values a lot more easily than with Solidity. And I found when trying to re-implement the code in Viper, it was at least 5 times faster as a developer to write the Viper code than to try and convert the Python code into Solidity, or JavaScript on the other hand. And once the Python code has been written, modeled, simulated, maybe in a Jupyter notebook, it's a lot easier to transfer that into a sort of standardized API, maybe on something like a serverless function like OpenFast, which we have actually done as a sort of proof of concept, and it was a lot, it proved very useful to extract any sort of business logic that you might need out of JavaScript backend, frontend, wherever, and onto a Python serverless function. So basically, once the code is validated, you can containerize it and ship it very easily. And this also allows users of your system, maybe the power users or developers interested in your system, to come and play with some of those functions. And this API is very, very basic, but the goal here was to see how quickly we could take the Python code and spin it up on an API. And the aim of what we would like to move towards is some sort of token engineering process where we model, simulate, and validate the code in Jupyter with cadCAD. Previously, we've been using Jupyter quite a lot to do a lot of our sort of basic bonding curve calculations, and it's proved very useful. And we'll talk a little bit more about cadCAD later, but it's Python based, and deploying API and contracts can also be Python based with Viper and the serverless APIs. So there's a benefit in this workflow that you're taking code that has been validated and you are trying to sort of change it as little as possible when placing it onto other layers of the stack. And then sort of the engineering workflow would be to take real world data and feed it back in and iterate. Another observation that we made was that when I was working with a few of the other team members that weren't necessarily familiar with math and how to understand it, when they saw the same code written in Python, it was a lot easier to work with, especially if it's in a Jupyter notebook where you can tell a story and have assistance along with it. So this is one of the observations we made when we were simulating the Protea token bonding curves. And currently we are using the token bonding curve where it's just a linear curve. But we noticed that this has some sort of abstract effects. So usually when you're looking at a bonding curve, you think about the collateral pool, the ecosystem value, and you see that there's 1 degree of freedom, which is the current supply. This can be simply represented as the current supply increases, the collateral pool increases. And whereas if you start looking at the user balance, you've got 2 degrees of freedom. You've got the current supply as well as the point at which the user bought into the system. So this can be better represented in a sort of 3D plane, which I'll show later, and also show the effect that, that the linear curve has, the negative effect. So yeah, when you break down a ecosystem and you start considering the users who concern themselves with DAI and potentially their return on investment in that DAI, a different story emerges. So our design objective was slow linear growth for users in the system. If a user buys into the system, you don't want early adopters to be given too much benefit. You'd like later adopters to also have a growth in their investment into the community. So if you've just got a curve of y equals mx, when a user buys into the linear bonding curve with a certain amount of DAI collateral, the gradient has no effect on their return on investment. And this I'll graphically represent a little bit later. If you have a straight line of y equals, for instance, example 2, the users will not get any return on their investment. But if you shift the linear curve up along the y-axis, you have the result that the return on investment can be designed for. And just keep this diagram in mind that the collateral under a linear bonding curve is the area up until the token supply that they've bought. So if a user buys 1 DAI, it will be represented by a certain area, and the same area will be for the next DAI bought. It will be the same area, just slightly less tokens distributed for that DAI purchase. So assuming a user buys into a community with equal amounts of collateral, let's say 1 DAI, the rate of growth is always the same, no matter what the gradient of your linear curve is. So if the first user buys in with Y DAI, they'll be given X tokens. If the next user buys in with Y DAI, they will be given another value of tokens. But if you take the first user and have them sell out later down the curve, after say 10 users buy in, they will have the same number of tokens, but their DAI value would have increased quadratically. So one of the things we saw was that with y equals mx, you've got a quadratic curve. By shifting the linear curve up the y-axis, your collateral curve. Yeah, so this is your bonding curve. This is the curve of how the collateral behaves in the system with token distribution on the x-axis and DAI value on the y-axis. The collateral curve changes such that you're using a slightly more linear part of the curve. And when we plotted this in the Jupyter notebook, so just to explain these plots, you've got the pink dot that represents the first user to buy in at a total supply of 0. And the buy-in supply is also 0 because they're buying in when the total supply is 0, and there's at this point the total supply is 0. Then if you move up to the green dot, this represents the return on investment at a total supply of 10,000 tokens. So you can see that if you look at this like leveling a playing field, right? Your first user is given a huge return on investment, reaching over 100%, whereas users further down along the buy-in points are rewarded a lot less. Whereas once you shift the linear bonding curve up the y-axis, you get this sort of more flat plane. There are still, yeah, well, this initial user is given about a 1% return on investment, which could be reasonable depending on what time period that is. But future users are also given a similar return on investment. So looking at this, so this was when we started simulating users buying and selling, maybe whales dumping, and using the cadCAD framework to sort of help us along. So these outputs from the cadCAD simulations, and we wanted to see what the effect of whale dumping in the system would be, because that's a real effect that you could see. In fact, I think we saw it in the first event that we held. So this is the die balance of a selection of users in system before and after a dump. So this is the first user. This is a user buying in slightly later along the curve. You can see how their collateral grows in value. And at this point, the first user dumps. There's a significant drop in the user's value. And this is, this is in a system where the user's collateral value should abstractly represent their dedication, reputation, or contribution to a community. And so you ideally don't want this effect. Now, if you take the alternative bonding curve, there is a slow linear growth. The sort of average day-to-day user is still given a pretty significant benefit. In fact, you can see that the effect of these, you can look at these plots and see that the collateral is more fairly distributed between initial users and later users. And here you can see that in effect. So when this user dumps, not as great an effect. So yeah, as we spoke about earlier, we've been using Jupyter for a while now. cadCAD sort of provides a framework for wiring up these system components and mechanisms and creating simulations around them, introducing potentially sort of random variables or doing various other experiments. And at the moment, the single mechanism we tested was the token bonding curve. We started introducing things like different user types, different ways those users might behave in a system. And cadCAD helps to wire up all those elements with your sort of inputs to the system, like your user base growth, various actions that users can take, like minting and burning, and the pool balance and how that is affected. So it's basically, we're trying to work towards a sort of more rigorous token engineering process by introducing simulation and taking a combination of the Jupyter Notebook with cadCAD to simulate microeconomies that we are creating with Protea Gather. And you've got to be pretty careful. You're dealing with real people's money, and it's good to be able to simulate these things on paper before deploying. So Jupyter for us sort of creates a way to tell a story. You can create your business logic and models, simulate it, view outputs, and iterate on that design. And you can easily share this with users and open source it for better collaboration. So you can't really see it here, but if you've never used a Jupyter Notebook before, up above this, we have various text explanations for these pieces of code. And then at the same time, you have the outputs that people can fiddle with the variables and see how that changes the design, which makes it very useful for onboarding people into how your system works. So some of the next steps that we would like to do is sort of extend some of the components of the system that we represent in Jupyter and cadCAD. So at the moment, with the token bonding curve, that would be a single component in the system. And in future, we can start simulating things like liquidation of communities if you want to do transfer to a new sort of community mechanism, maybe a different tax rate, or if you wanted to start looking at events and how users interact with events, you can add that as another component in the system. So we also reached limitations when using Solidity, so we're going to look at re-implementing some of the math in Viper for future. And yeah, Michael from BlockScience is on the call as well, and he's going to go through cadCAD probably in a bit more depth, or if you've got any specific questions about that. Otherwise, if you want to see any resources, links to repos or notebooks, we can also send those your way after the call. Cool. Any questions?
I mean, personally, I'm just thrilled to see the cadCAD and the methodology in practice outside of my own team. I've been working on putting it together and building educational material for a while. I think this is the first time I've seen a presentation where like someone just like does it and shows other people. So it made me really happy.
Awesome. Great to hear that. Yeah, we found it a really useful tool. Just in general, you know, before this launch, we hadn't really gone through the process of auditing code, modeling it, really considering what the effects of different parameters are. And leading up to the launch, we were pretty serious about trying to audit this code and model it. And it was a very useful process.
Thanks so much. There's no questions in the chat for you at the moment, but if you guys do have any questions, you're welcome to also just unmute yourself.
Cool, awesome.
So I realize it's rather impromptu. Fathom, be quiet. It's rather impromptu, but I have some presentations on some of the stuff that we've been working on in cadCAD for the common stack. If you guys want to see some other work in the framework, it's going to be Jupyter Notebooks if you're interested. I don't want to like hijack the second half, but it sounds like it was open and
it is open, and you're more than welcome to have it.
Cool. So let me know when you're ready. If there are more questions, please ask them before we shift.
No, I think we're good to go.
Cool. Then I will screen share. Let's see. Go here. Switch to motivating. So can you guys see my screen? It's a diagram in
Yes.
Lucidchart.
Yeah, okay.
Cool. So I'm going to motivate the system that I'm going to talk about in cadCAD by this picture. So the brief summary is that this is an example or like a reference design for what I call a cyber physical commons, which is a system that's job is to coordinate people through a token to produce a material output as a group, and that ideally that material output is valuable outside of that group in such a way that results in sort of sustained economic flow for the group itself. So to sort of dive into it, the left side, this black bar is you can think of it as the permissible boundary of the system, and that's where the bonding curve is. So the logic relating the reserve and the tokens is going to be a bonding curve. I'll talk a little bit more about my choices along this preliminary design in the Jupyter notebook, but the key is that the role of the bonding curve is to serve as a sort of cell wall between this community, this organization, this local economy, and this like kind of outside global economy. And then when there are tokens, we can think of them as being sort of influence or at reputation similar to what the team described. And in this particular system, that is used for decision-making through process that we've been calling conviction voting. It's based on some sensor fusion principles and some research of mine from actually back during my PhD. I worked on decentralized optimization and estimation. And this is an attempt to filter out the underlying preferences of people in a meaningful way without having batch time box voting. And in this system, that process determines the release of funds from a funding pool into proposals. And this mechanism is called a trigger valve. For now, we can think of it like a neural network firing. The information coming from the conviction process is going to determine whether a condition is met by which the funds for that proposal are actually issued to the proposers, which are then only released contingent on sort of completion of milestones in those proposals. And this whole engine produces material outputs so that we would hope that it would be valuable enough to continue to sort of fund itself. And so we can imagine this for, say, open source software or research or other types of outputs that are sort of community driven. Anyway, so this is the gist of it. It's a like living design, but I hope the diagram helps give a sense before I open up a Jupyter notebook and sort of show you what that looks like for me in cadCAD. Any questions about this?
What software did you use to draw it?
Lucidchart.
Wow, beautiful.
And I've been working on this with Abby, who I believe you guys know. So I had the original design and she's been helping me refine it. And if you actually look over here, it's a ton of notes that she and I put together regarding sort of the nature of resources in this sort of hybrid, like it's not really commons or it turns out that blockchains blur the lines between the traditional notion of goods, and so I've been exploring that concept. And I think Chris Peruk is also on the call, who's someone who spent a lot of time talking about the relation to sort of economic canon versus what happens in these systems. So anyway, let's jump to cadCAD. So I'm going to jump to the top of this notebook and sort of give you the quick overview. So in this system, we're using cadCAD. It's in a public repo, although the people in the cadCAD beta can run it because this is available. Obviously, we're working on getting cadCAD out to everyone. And if you're interested in that, you should check out the Common Stack stuff. This system is characterized sort of first and foremost by that trigger function, actually. So this function is actually a parameter in my cadCAD model so that I can change it and look at how the changes affect it. And this is going to be the conditions under which a refunding request passes, or that neuron fires. And it's actually a pretty simple function. And to your point previously, the Python makes it fairly easy to read. You have a certain amount of funds requested by the proposal. The system has a total amount of funds, and there's a current token supply. These parameters, beta and rho, help me sort of parameterize the function, because beta is this barrier function. It means you can't remove more than beta of the total fund with any one proposal, because the required conviction goes to infinity. And I'll show that in a plot in a second. So this is linear in supply. So if you go to the bonding curve and you mint more supply, the requirements for passing your proposal go up linearly. So you can't just go mint until it passes. And then no matter how much the conviction you have, if what you're requesting is greater than beta %, you will not be able to pass it. And this is my sort of, let me see if I can zoom in a little bit. Here we go. So this is my heat map of the trigger function, with the dimensions being share of funds requested and the total token supply. And this is the amount of the amount of the trigger. And so it's scaled by log 10. So this is saying you need, 10 to the power 5 conviction, which we'll talk about what the units of that are later. If you are at the far left and you need, this is 10 to the power 13, and this is actually diverging to infinity. That's just the last data point. So that red on the side is that infinite divergence. And it's tricky to do plots in 3 dimensions, and I like using heat maps because they're easier to read than trying to put a field on a 3-dimensional axis. I also take that same plot and I show the relation to alpha. So alpha here is the sort of conviction sort of charge up rate, but it also sort of encodes how much it charges up to. So conviction is a way of counting voting that accounts for both time and tokens. It's actually essentially like a capacitor charging. So once you sort of say that you're supporting something, you are basically getting the power of that support accumulating over time on this sort of like quickly rising and then leveling off. And this is created through a discounted integrator. It can be computed step over step and iteratively. And it actually works quite well for synthesizing noisy signals. I say it's a discounted integrator. It's fulfilling the role of an integrator in estimation theory. So it's going to basically say the higher alpha is, the more conviction you're going to be able to accumulate. So the maximum possible conviction is actually higher. So this plot basically tells you what share of the possible conviction is required to pass. And it's important to note here that this 0 on the heat map is actually the largest possible passing. So you can't have more than 100% of the possible conviction in the system. And this means that it's actually only the blues that are actually possible, not the greens. And this tells you that even though the upper bound is 20%, that the practical bound is actually much lower. Here it's going to be about 10%, and in fact, that's still a bound. So we're looking for proposals that really pass to be in the sort of, potentially 5% or less, with the sort of 10% being everyone backs this, and 20% being the formal mathematical upper bound under like any condition possibly passing. And obviously this is important because no matter what the group decides, we can't have this system dump all of its funds out quickly. Like no amount of collusion or sort of even real, genuine everyone supporting something will allow the system to just divulge all of its funds at once. So then we're going to kind of get into my cadCAD model. I've pushed a lot of the functions into helper files. So for starters, I'm just initializing. I'm going to have 60 participants in my simulation, 3 proposals initially, and then I'm going to start my system with a sale price of 10 cents. The bonding curve that I have in my model follows the hatch principles outlined in Abby's deep dive article, which means that it's not actually going to be started at 0. It's going to be started at some point live based on the initial investors. So there'll be a sort of a hatch condition, and that's going to result in an initial return, a paper return for the participants in what is essentially the hatch sale, and then like follow the bonding curve starting from the initial condition point. So this is the sale price for the initial conditions. And just as a short note, like I'm importing this set of equations, which is just a bunch of Python logic that matches what's in the augmented bonding curve analysis. So I can not have to go through them all in this notebook. Let's see. So I'm going to initialize my system. I'm going to kind of jump ahead to pictures to show you guys what's happening. So my system has a multi-graph as its core state. That means that it has proposals and participants. The participants have a graph that represents their influence on each other. The proposals have a graph that represents their conflict with one another, meaning that technically the system allows you to pass every proposal, and it's going to be driven by the decisions of the participants. However, some proposals are unlikely to pass after other ones because they cover the same topics. And so we use a conflict graph. So I generated data about the sort of overlappingness of the proposals as a way to represent this. And then sort of basic setting up these experiments, you'll do things like generate holding distributions. This is generate the funding requests. This isn't too interesting because there's only 3 of them. The model that I'm going to show you, though, new proposals and new participants arrive. So I wanted to start this small because it actually grows over the course of the simulation. There's some important underlying information now. Again, this is a little bit fat because I only have 3 proposals, but I generate the private signals of the individual participants regarding their preference or their affinity for the proposals so that I can have a sort of locally logical heuristic for people's behavior. They're going to basically support things that they like and or that they like because their friends like. These are models that can be expanded and improved, but for starters, it's nice to have those mechanistics in the state so that they can become part of the decision logic in the cadCAD model. I set up a group of parameters. So one thing to note is that cadCAD contains equipment for experimenting by changing parameters. Here, I've defined alpha in terms of conviction capacity, and that just basically means the multiplier of your tokens on conviction. Since conviction accumulates over time, it does accumulate to a factor times the number of tokens. And if you set that factor to 2, that implies an alpha of 0.5. If you set that factor to 5, I believe that's 0.8. And 10 is 0.9. And so there's this exponential relationship between alpha and the sort of conviction capacity. And I've set this list here. So when I run this experiment, I'm actually going to get 3 separate runs. Each run is going to be 10 time periods. Excuse me, it's going to be 100 time periods. And I'm only going to do 1 Monte Carlo. And then when I package this up to simulation parameters, I have these dictionaries that tell me all the facts about my run so that I can store them. Like if I store the data, I have a header that tells me about that experiment. I have my initial conditions defined, and then I have a logical walkthrough similar to what we saw. Here I have my first 2, we call them partial state update blocks. Here I have the arrival processes, randomly generating new participants and new proposals, updating my state variables. And then I have checking the progress of proposals that have passed previously and updating my state variables. Then I have the systems policy. This is the mechanism that we've designed, the trigger function. And so we check the state of the system. We pass anything that passes the trigger function. We update the state variables. And then finally, we have the decision block, which is, this is going to characterize looping through all the participants in my state and actually allowing them to sort of make choices, buy or sell on the bonding curve, depending on their sentiment and their affinities for the projects that are available, and also potentially assign tokens differently. So we generally assume that the behavior is somewhat asynchronous. One of the goals of this system is to take away this sort of time-boxed effect on decision-making where you have to be available at a specific point in time and aware at a specific point in time to be effective. So the participants can actually, make adjustments to their preferences, sort of kind of wake up and do it whenever, rather than say, here's a vote, you have to come participate right now or your influence is lost. So there's a variety of things in this block, in the sort of helper file, describing how decisions are made and what decisions are made. I will say there's a lot of room for us to iterate over that. I would say there's a relatively naive set of logics there right now, but we can do all sorts of tests, like even adding additional patterns of behavior where we could have some honest actors with one set of decision functions and then another set of actors that's sort of undertaking a collusion attack or a vote buying attack. This system is actually designed to be relatively resistant to both. Vote buying is not particularly meaningful in a system that doesn't have a specific trigger time, because things get slowed down. You're essentially renting, and at that point, you'd be better off just going to the bonding curve in most cases. But we do have to do quite a bit more analysis to sort of bound that effect and to figure out what parameters make that sort of make sense. So I run the simulation in cadCAD. This outputs 3 sets of results. Quickly, the first one, I just high level, first one is not really passing anything, so the funds are just accumulating. The alpha was too low. The second one, you see some disbursements. The third one, you see some disbursements. This isn't really a good summary. It's just like a quick check, because I got to dive into one of them to really show you anything interesting. So I'm going to set the experiment index to 2, which is the third one. So I do some sort of data science style processing, pull a bunch of the data out of the data structures. It's important to note that in order to keep these systems efficient from a coding perspective, I use NetworkX. It's essentially like having a graph database in memory. So if I'm trying to build a model around a concept that's highly representative of a network of agents, then I use this to represent agents, and actually agents and proposals in the graph structure. It makes the system modeling a lot easier as the sort of complexity of the concepts you're representing grow. But afterwards, I have to unpack them out of that graph structure, put them into data frames, which are essentially tables, so that I can sort of examine them. So I'll focus on pictures. So this is a decent summary of the local economy. It basically just says that the funds, reserve, and supply stay more or less in their order of magnitude. And actually, this is dual axis. The price in this system went from about 0.39 to about 0.46. I guess that's maybe closer to 0.48. This growth was only about a few cents, but the key here is that I use this initialization trick where the early adopters are essentially initializing the bonding curve, and there's it's a little bit related to what you did with your offset, except for that I created the offset through initial state like math tricks. So the early participants pay 10 cents a token, and then that 10 cents of token gets them tokens and it fills the reserve. But then if you were to just exit that out, you would go down the bonding curve and you wouldn't actually be able to like fund everyone getting back exactly what they put in, because the integral function that you were talking about before. So two things that we do is, one is force vesting. So anyone who participates in an event that creates paper gains immediately doesn't have the right to exit them immediately. There's a period over which they can, they become vested. And this is similar to sort of a VC round where you get sort of paper gains, you have a post-money valuation, but you're not in a position to immediately exit it. And therefore, the system can kind of realize the benefit of your initial capital infusion, but in the long term, you will be able to slowly, get the returns that you earned by bootstrapping the system. I can always go into that in more detail some other time, but I think both Abby and Jeff are working on articles to sort of express those concepts. My bonding curve in this system actually, let me check what my bonding curve was. It's one of the parameters, so should be up here. Okay, so I used a bonding curve with curvature 6. This is pretty aggressive, and the reason this run had curvature 6 is because I wanted to show that in practice, high curvature bonding curves aren't nearly as Ponzi-y as you would think, because that curvature represents a resistance. And so what you end up getting is something that stays pretty tightly in its linear, in a locally linear behavior, not because the curve doesn't curve a lot, but because the fact that it curves a lot produces a lot of resistance to moving along it. And so the actual behavior stayed pretty local. It costs a lot of money to move along the bonding curve. So if you initialize the system up the curve, no one ever gets the really early sharp curve, kind of like in the previous example. And then once you're in a spot, then going down the curve would mean quick losses, and going up the curve would mean quick losses. So incidentally, when you loop it into a system model, high curvatures actually tend to result in very little movement along the curve because of this resistance. And obviously it comes down to how you model people's behavior. Certainly opportunities to expend large amounts of capital to move things up the curve. But I was exploring the effect of using invariance with high curvature. The invariant that was used in the previous presentation had curvature 2. So this is 3 times as much curvature. I can also run this with that curvature. I define bonding curves literally in terms of their curvature, because that's the thing that defines their characteristics. And what we see here is the yellow line is the sort of mathematical representation of the price curve, and the blue dots are the points in the simulation related to the actual observed values at each time step. I have one for the price curve and one for the invariant curve. I refer to the phase space representation as the invariant. That's the thing where you say supply, a function of supply and reserve is equal to some constant. And if that holds true, that's how you can derive all of the minting and burning and price functions, basically all directly from that function. It's explored in Abby's deep dive on bonding curves article. I'm gonna try to wrap up so we can answer questions. This is a affinity plot at the end, so there's many more proposals and many more participants. So we are generating more and more private signals. The system's overall flow was that there was new proposals arriving. Some of them get passed and they become active. Later on, some of them turn green and get completed. I also include random possibilities of failing and killed proposals and ones that don't have enough support. So they were candidates, but then their support dropped out. And so we view them as no longer candidates so that we don't spam the system with lots of unsupported proposals. Sort of the coolest plots, this is a lot of my exploration. So I think these are the best plots here. They sort of show participants on the left sized by their amount of holdings, proposals on the right, color based on their status, and the red lines across are the support of the users for the proposals. And I can run this I can make this plot at every point in time in the cadCAD simulation, and you can see they're sort of charging up in percent conviction. When something blue hits 100%, it turns yellow, and if it gets finished, it turns green. I've been like playing around with even making videos of this system. And so the high-level summary of the conviction accumulation here, this is just the percentile since there are many proposals, and this is the sort of passing. So I'm saying these are the distribution of conviction as a share of their trigger functions, and each time this purple line crosses, it's basically showing you that the highest one across the line, it's generally precipitated by something passing and therefore dropping. So I won't try to go too much into the specific plots here, but this is kind of what the workflow looks like for a pretty big complex system with a lot going on, where it's not immediately clear how the different mechanisms will interact with each other. And we want to basically use this tool to help us say, okay, well, how do changes to the bonding curve, say, affect the way that conviction voting is going to work, and vice versa. It's very difficult to do multi-mechanism design without computer-aided design tools. So that's the end of the sort of presentation. Do questions?
Thank you so much, Michael, for the presentation. If anyone has any questions, you're welcome to unmute and just ask.
I think having gone through that design process, obviously at a lot less complex scale, a lot of answers have been given, but also, can learn a lot from your workflow, and excited to working with cadCAD more.
I can post the link to the repo. So this is actually in a public repo. So actually, if you want, I can grab a GitHub link. To be fair, it's admittedly not super well documented, and I've been fortunate enough to have collaborators sort of helping me take my work and organize it into more sort of approachable blocks of content.
I had one question about, you were speaking about if there's like 100% support for something, then it's still not possible for a certain thing to be actioned. I was just wondering if you could speak a bit more about that.
Sure. So the way that the system is designed, it's designed to have good properties in time in addition to having good properties in sort of the short term. So you can imagine that the current funding pool is some amount of money that's meant to be sustainable. And so you don't want, even if everyone in the current system is 100% behind something, for them to be able to basically issue the entire funding pool to something, because that's essentially sacrificing the future of the system. So sustainability, like designing for a sustainable system, means including in the way that you design it, even the relation between me today and me tomorrow, or my community today and my community tomorrow. And so the system actually has an upper bound parameter for the maximum amount any one proposal can issue, even with maximum conviction. And that's because the conviction required is going to go to infinity. If the same proposal were shrunk to be a smaller percentage of the total funds, or if you raised enough funds that it was no longer of that high of a percentage, you could pass that proposal. So it's really about bounding the means of depleting the capital pool, and it's a tunable parameter. So I mean, we could make that. I mean, technically, if you made that 1, it would be ineffectual because it would mean that you could, in fact, release the entire funding pool. But I've been playing with something around 20-25% as the hard bound, and using so that results in something in the 10 to 15% as the like amount that the whole community could pass. And to be clear, this just results in potentially needing to make multiple proposals. So there's this notion still that like you could make multiple proposals that issued that percentage. So it creates a sort of decaying effect where if I could release 20%, then I could release 20% of that what's left after that, and then I could release 20% of what's left after that. And it kind of creates this effect where, you know, it's called like a Zeno's paradox, right? Like no matter how many times you release a percentage of something, some of it is always left. And that trick is there to, again, sort of parameterize and help spread out the sort of temporal effect. And since we have these other slowing processes on the voting side, we are essentially bounding the rate at which the system can be depleted. It certainly could be depleted, but you have to basically support things. Your support has to charge up, and then it has to pass, and it's going to pass, say, 15% of the funding pool, and the community would have to say, do that again, and sort of drop the funding pool out. And again, the important thing here isn't really that you can't spend it all. It's that there's this like built-in integrator that's like giving us hard bounds on how fast this can happen.
Thanks a lot. That makes a lot of sense.
Hey, hi. I've typed a question. I have a bad French accent, so maybe it will be hard for you to understand, but my question is written in the chat.
Okay, let me see.
Sure. So the question is to remove, sorry guys, to remove Ponzi schemeness, what about financial management of the collateral pool and increasing the collateral pool with profits generated by the underlying project?
That's a good point. So there's a couple different ways to wire things together. And one of the things I'm going to say is one of the early things that I like played around with some of these ideas with was Simon's project with Autonomous. And I was like wiring together different ways of thinking about bonding curves. And even there was a, annotation for the conviction voting. And in that example, I very much had my versions of these drawings had funds going into what was essentially the collateral pool. And I think that makes a lot of sense. I think the better way to think about it is that there's not one way to wire these things together. And when you wire them together differently, you're going to get different systemic properties. And so in a system that's going to generate profits rather than like grants and stuff, like I would think that would make more sense to put it in the underlying collateral pool. But in the design that I showed, which I will pull back up, one of the differences is I have a separation between the concept of the funding pool and the collateral pool. So the reserve in the lower left is the funds under the bonding curve, and the funds that are actually available to issue to proposals is a different pool of funds. And they're related because anytime someone burns, they're going to pay an exit tax, which is going to flow into the pool, which is a bit like what you see in the difference in prices in like Tybald's work on continuous organizations, where you have a different price in and out. In this case, it's a different price out because you're going to take a 1 to 2% tax on your on what you would have been able to withdraw. That 1 to 2% of it goes to this pool. So my answer is really that I think what you're proposing makes a lot of sense, and I think it's just a slightly different system design. And my main thrust with the Common Stack work is actually not to propose a specific architecture, but rather to help build out the frameworks for people to design their own architectures that meet the needs of specific communities. Because my feeling is that there really isn't a one-size-fits-all solution. I think of this a lot like, almost like buildings are architecture. They're housings for communities to do things. And so it's really the community that kind of determines the needs of the building. And we're making these sort of digital workspaces for communities. And the one that I'm showing you is different from the one you're asking about, but I think the one that you're asking about is also well-defined.
Thanks, that's very well said. Also, I have a question for the next one, or the next talks. Is it possible to include a lawyer and to talk about the regulatory framework around bonding curves? I'm very interested into the practical business applicability of bonding curves in the current legal framework.
Sure, that's definitely something that we could look at sourcing a speaker for. I don't think I know anyone at the moment working in the space, but if you guys have any recommendations or anyone on the call that we could maybe...
I mean, I've been talking to an IP lawyer in France from Linklaters, but you know, regarding those type of topics, I don't find them super sharp. So, and I know that you know, to be really something that exists in this world, the legal component, the regulatory regime is important. So the notion of property is kind of complicated, depending on where you are, common law, civil law. I mean, there are a lot of things around, and I kind of really like bonding curves, but I'm scratching my head and wondering how it goes when you look at it from a legal perspective.
I think that the concept is also still quite novel as well. I mean, it's the same as regulation around any of the tech like DAOs or basically anything blockchain is also still like regulatory up for discussion. But I'll see if I can pull somebody into the call for next month.
Okay, thanks.
Thank you so much to Ben and Michael and Wayne for your presentations today. I found them all very interesting. And thank you very much for everyone who attended. We've just hit 8 p.m. now, so I think it was a very good and interactive session. Yeah, if you guys have any feedback as well, or if you know anyone that would like to speak in the next call, please drop me a message.
Thanks so much, Devin and Michael, for presenting.
Thank you.
Okay, bye guys.
Yeah, thanks guys. See you again soon.
Cheers, everyone.
Thanks, guys.
Bye. Bye.